All right, so nice to meet you all, yeah. So I would like to start with thanking the organizers. As the final speaker, I feel like we should give them a round of applause. They did a great job. And let's dive in then. So I probably should start with saying that the title is Python Meets the Crab, Friendship at First Sight. For those of you who don't know, the mascot of the Rust programming language is a crab, hence the pun in the title. So as you might deduce from that, we're going to talk about Rust today. So I hope you had enough of Python, because now you can learn another language. All right, so first to introduce myself. Yeah, I work at Bloomberg, and the t-shirt didn't give it away yet. And I'm also an open source contributor. I have quite a few projects I contribute to. I'm a member of the Python Packaging Authority as a virtual env build maintainer / author. And more importantly, I'm husband to a beautiful wife, Lisa, and parent to 2 Yorkshire Terriers, Silky and Junior. And I'm going to show them throughout this presentation. As a proud father, you must put up with it. All right, so I'm originally from Transylvania, which is kind of like there in middle of Europe. So hence my weird accent. So again, another thing you have to put up with it. Now, these are some of the projects I maintain. As you can see, all of them have various popularity throughout it. But for this point of view, for those of you who don't know, I do maintain this tool called pyproject.format, which formats, never believe it, your pyproject.tom file. This actually is written in Rust, so that's kind of like my experience with using Rust from Python. Now, I also encourage you as kind of like an answer or kind of like a best practice, never be afraid to ask a question. I might not be able to answer your question as part of this talk, but come to me after it and I can answer all your questions. All right? So let's start with the obvious. What is Python? If you don't know what it is now, you must have had a very weird last 2 days because you have no idea what's going on. But, so to say the outline, it is an easy to read and write programming language. Has a garbage collector. What this means, you don't have to worry about memory. It's also an interpreted language, though kind of like an implementation detail. It does have a compilation phase where your Python code gets compiled to a virtual machine code and that gets run. Anyway, you don't really care about that. It just works. Now, more important, it's optionally typed. We had the talk earlier who demonstrated how you can use type to make your code easier to read and write. You can use it. The interpreter, again, doesn't care. It's up to you. It's totally optional. And another big kind of like statement of the language is that it uses exceptions for error handling. While you can use return values, it's not really built for it. You should use exceptions. At least that's the core design principle of it. And also does a bit of functional object-oriented programming. Again, these are only stuff you learn in computer science. Doesn't really matter afterwards. Now, let's look into the more important one. What is Rust? In order for me to tell you how you can use Rust from Python, we first need to understand a bit what Rust is, how it works, what is their core design principles. So I'm going to have a few slides where I'm going to kind of like demonstrate, if you know Python, what is the biggest differences when it comes to Rust. So Rust at its core, it's a programming language created by Mozilla, released around 13 years ago, but it primarily emphasizes performance. What does this mean? Is that it's not an interpreted language. It actually compiles to some binary code. So then you can get this, have to put up with these things called compilation, which just takes time, but you get in, as a benefit, great performance. It's strongly typed. What this means, now you have to care about types everywhere, all the time, even if you don't want to. For example, here you see we defined a short method. That method has a argument, you have to put a type. That's a return, you have to put a type there. It's also concurrency. It wants to make concurrency easy. What is the biggest enemy of concurrency? Mutability. If everything's immutable, concurrency is much easier, because there's no such thing as race condition. Because, hey, nothing changes ever. So for that reason, Rust, by default, everything is immutable. If you want to make something mutable, you have to actually write some code and make it tell to the compiler that, hey, this is mutable. All right. So now let's look some of the outlines, let's dive deeper in it. One of the core kind of like Rust things that coming from Python might be totally new is that Rust has this concept of unrecoverable error. They call it a panic because when this happens, you panic together with the program. And there's no way to come back from this. This is basically just shoot down, that's it. That's for the day. As you can see, when something like that happens, you get a lovely stack trace, but that's about it. Another thing that it does is macros. What is macro? Macro, end of the day, is just some concept that allows you to take some code, and in the background, the compiler makes for you some other code. Why is this good? Because you can basically specify quite complex things and just write it very succinctly. For example, to print to the standard output, you can use the println macro. You know it is a macro because every function call that ends in an exclamation mark, it's a macro. So that's why you can see, for example, here, to create a vector, you just specify an exclamation mark, and then at the end of the day, the Rust compiler will do some code mangling and make it happen. How it make it happen? It's an implementation detail. You don't care. All right. So another big thing is it has no exceptions. Rust doesn't know what an exception is. Instead, it uses return values, primarily these two built-in time calls, option and result, to specify if something happened as we expected it or something blew up and some error happened. Now, the option is kind of like, for example, when you would look inside the dictionary, then you might get back, no, that key might be missing in a dictionary. That's why you have an option. And then the result is when basically some error that kind of like something failed, but it's not kind of like expected. So as you can see, both of them have kind of like a success and a fail type with the OK and error. And the option is like just optional where it's a none or just missing. Now, another thing that you will see from this, that Rust also very much like that to not have parentheses around your if statements. Those are kind of like optional. That's why on those if statements you see I can just not put any parentheses and it still works. That being said, it is not an indented language. So I hope you like curly braces very much because you're going to have to get a lot of them. All right? Now, another big difference is that Rust doesn't do object-oriented programming, at least not the way you know it. Instead of classes and inheritance, it does what they call traits and implementations to it. What does means that in order to define kind of like a data structure that holds some data, you do that top line, the structing, and then in data structures, you can then define interfaces, which they'll call traits, and those traits can then be implemented by the class itself. So that just kind of like, once you start doing it, you have to like rewire your mind to think in that concept. Another thing is that everything is immutable by default. If you like to create a vector and you try to add an element to it, it's going to fail. The compiler will loudly shout at you. Instead, you have to do this magic keyword called mute. And if you define something with a mute, that just means, hey, this is mutable. And then you have to deal with whole other problems. But now at least it's mutable. All right, another thing that you're going to notice that Rust also has this concept with every method, the last statement is returned by default. So you're going to not see often this return. Instead, you're going to just see this, which basically just means if there's no semicolon, it's the last statement, it's automatically returned whatever is inside there. All right? And that's pretty much it. The final thing I have to say as a packaging person in Python, that Rust has its own packaging called cargo. Actually, UV was modeled after cargo, kind of like one tool to rule them all. And when it comes to packaging, Rust has this concept of a crate, where a crate is the smallest concept that the compiler treats at a time. You can think of it basically as a library, but it can also be like an application. So with all that jargon out of the way, we're ready. We're ready to actually dive into how we do Rust from Python. So let's start with, why do you want to create this friendship here? Well, because Rust is fast. Python is very great. We love to use it and write it because we don't have to worry about all the nitty-picky details. But it does mean that occasionally we run into a situation where Python is slow. You don't have to throw out Python in this case. You can just basically replace the performance-intensive part of Python with some Rust code and get all the benefits of both languages, basically, with some pain point of trying to make the two work together. So another reason why you do want to potentially use Rust of reliability. And this is because whenever the garbage collection in Python runs, you're going to have basically some time window when the Rust when the Python garbage collector will basically pause the entire interpreter. Nothing happens. Now it's the garbage collection time. This is not a thing in Rust. So for example, when the Granion, which is kind of like an alternative to Greunion, the G-unicorn, was written, one of the Granion is kind of like a Rust application server. When this got written, didn't really have much spikes when it comes to latency. It's kind of like very stable all the time, just runs with a very low latency. All right? Another thing you might want to do is feature reuse. For example, I wanted to write a TOML formatter, and while Python has great formatter or great libraries to write TOML files, you can't say the same thing when it comes to write Python file or TOML files, especially if you care about comments and keeping the style and all that kind of stuff. Luckily, Rust does have a great library called Taplo, already implemented it. So you can basically use all the Rust functionality and all the implementation of the Rust libraries in your Python code with very little effort. Okay? So now you can use not just all the pypi.org, you can use all the crates.io, which is the Rust version of pypi.org. Another thing is that you have a slightly easier security model than C. This kind of like comes from the memory management ownership, because the compiler itself kind of like defends you from a lot of the security holes with pointers and all that kind of stuff. If you start writing Rust code, your code will be suddenly much more secure on average than if you would start using C. Now, this doesn't mean Rust will not solve your security problems. It's very much still good and easy that you can write big security or serving application. It just makes it harder to get there. Okay? And finally, concurrency. Free-threaded Python is around the corner, but until we get there, Rust can solve all that problem for you. All right? And maybe the biggest selling point is that you can experience both the joy and misery of writing Rust code. We all know that Rust came just about ahead of Python when it comes to developer joy when writing it. So now you can do that. So the kind of like the glue between the two languages is this project called Pyo3. This is the mediator. This is the thing that makes the two languages able to talk with each other. It offers you two functionality. You can call your developer Rust code from your Python code. You can do that. Works the other way around too. So you can actually call Python code from Rust. The two languages. This is, for example, very useful. Let's imagine inside your Rust code, you want to call a standard library function from Python or one of your own functions. It is able to be all back and forth between the two languages. You don't have to like have a clear isolation between it. So it primarily takes transition between this. It's kind of like the translator of between these two languages. Now, for those of you who came to my tutorial on Thursday, you probably learned all about packaging and backend and front end. But the short version of this, the way the Python packaging works, you have a front end, the one that you communicate with. This is usually like pip or UV. And then you have a backend, which actually spits out the artifacts that you upload to PyPI, or an artifact that you kind of like see that you interact with or install. The kind of like this backend that does this for the Rust code, it's called maturin. This is kind of like a child project of Pyo3, but you're going to see references to this project really because this is the layer that actually compiles Rust into Python release artifacts. Okay? There are alternatives to it, but for all intents and purposes, most of the people just use maturin. Now, this is the carrot part of it. Do you want this? Is it this production ready? Well, here you're going to see some of the most popular projects that already use Pyo3 to release their Python artifacts, or like to release fast code to your Python interpreter. You might see some of the more popular ones, like Pydantic, Orgison, Rough, UV, Polars. All of this already been using it for the last, I don't know, 2 years. And I don't hear anyone really complaining about any of those projects. So yes, it is production ready. It works great. It is popular. So how do they do it? Let's get into that part, okay? So in order to actually be able to demonstrate how it works, I'm going to quickly bring up a use case. The use case is we're going to want to find the first n prime numbers. What is a prime number? It's basically a number that's greater than 1, and it's not divisible by any other natural number. Here you can see kind of like a quick example of it, and for example, the first 5 prime numbers are like 2, 3, 5, 7, 11. Here is, for example, a simple Python implementation of it. This is something that we could write. Basically, we create a list, then we iterate over every number starting from 2 until we get enough prime numbers detected, and then we just check, hey, do we do a for loop? If any of the previous prime numbers divides it, then we avoid, and if none of the previous numbers divide it, then we add it to our prime list, okay? So this is like a quick and simple implementation of that. So, how this is going to look in Rust? Well, this is a Python, not the Rust one. This is how it looks in Rust then. As you can see, it got just a bit more complicated. For example, now our interface has some type annotations at the top of there and has some slightly curly braces, but we have the same result, which just starts with no elements in it, and at the end we return it, hence why there's no semicolon there at the result. Then we have a while loop. Then we have that variable that we start at 2 and we just keep going up. Then we have this for loop that has this end character, but not that important, iterate over. And because Rust doesn't have the lovely else in a for statement, we actually need kind of like a flag to keep track of, hey, did we already, is any of the numbers kind of like divided it or not? And if not, then we just add it into it. All right? So if you look at it from that point of view, I guess we go back. You can see that if you call your friendly new overload called generative AI, it's not too complicated to transform your Python code into a Rust code. If you get a bit of experience, you might be able to do it yourself after a few days of kind of like playing around with Rust. All right? So, how do we expose now this Rust code that we've written inside Python? The way we do it is we use PyO3. I decided to this ellipses inside the first method. I just removed those, got the actual code that we showed on the previous slide, but for brevity and easier to see on the slide, I removed it. As you can see, PyO3 uses this thing called procedural macros. What is a procedural macro? Well, it's that thingy inside that hashtag and the square brackets. It's basically the normal macros we learned at the beginning of this presentation on steroids. It rewrites entire bodies of methods, not just kind of like a single line. Anyway, implementation detail, basically you use that to kind of like configure your methods. For example, here you can see that we use this py function procedural macro at the head of the method. We just explore that, hey, do we want to kind of like publish this method for the Python layer? And then we define kind of like, because in Python methods lives inside modules, we define here that this magical method gonna live inside this underscore lib module, and it's gonna be a module, and then we have a body where we like manually add that Rust code or function into the module itself. All right? This is code that you can just copy from the documentation, but this is the idea of it. Okay? Now, then you will need to define some packaging logic so that the Rust compiler know what to do and how to do it. This is what you would call the PyProject.tom variant inside Rust, the cargo.toml file. It's a toml file the same way. You see inside the package, we have kind of like just overall project description, which is not that important ultimately. What's more important is this lib dependencies and feature sections. Inside the lib section, you can see that we basically specify that, hey, this is where our Rust code that we want to expose lives. We're going to expose it under this name. And then inside the dependencies, we say, hey, tell to the Rust compiler that you're going to want to use PyO3 to actually achieve this packaging logic. And the feature segment is just something that's added for now. I'm not going to explain it part of this presentation. But basically, if you just add this, I don't know, 19 lines of cargo.toml file, and you have a cargo file, that's all you need to do, more or less. You need to slightly modify your PyProject.tom file. Instead of using setup tools or hatchling, now the build backend gonna be maturin, where you specify, hey, this is the backend, this is the actual Python package that does the packaging. And then there's another section inside your PyProject.tom file that roughly exposes which package should this module live in, and which is the file containing the Rust code or packaging configuration, stuff like that. But once you do that, you can see I can just put in my Python file from primes_lib import x, and it's just gonna work. That's all you need to really do. Then now it's gonna be exposed. So this is gonna be your final project layout. These are the Rust specific parts. As you see, cargo uses by default a log file, hence why you have this cargo.log, but that's automatically generated for you. You don't have to think about it. At the end of the day, really, the only two files you have to create is the cargo.toml file and that Rust source file. And the rest is basically all your normal Python files, all your Python projects. Yeah? And once you do that, and then you just call Python pip install, everything will just work, and the backend will take care of compiling it. Great. Now let's see, was it worth it? If I use here Hyperfine to benchmark the two implementations, you see that the Rust one is on average 13% faster than the Python one. So if you care about the 10x performance improvements, probably worth it. Obviously, depending how complicated your Python logic is, you can get more or less than this. But it's definitely, with fairly low effort, you can get a bit speed up if you need it. Okay? So let's look briefly into how does it work. How does it work? And I'm going to go briefly over the import system. Basically, the way Python import system works, it doesn't really know if something is importable or not. Instead, it always uses the concept of it is easier to ask forgiveness than permission. So long story short, Python doesn't know if something is there or not. Instead, it's going to use the import system at runtime to make a judgment on it. And the important part for our topic here is this Pathfinder class, which is the importer that is going to import the Rust module. And more importantly, here at the end of it, we're going to see that this Pathfinder is actually controlled by this sys.path system variable, and it's going to try to import any file available at those given locations. And this final to us with what we call side packages, third-party libraries that you install. Yeah? So if you look into your side packages, once you pip install your library, you're going to see that inside this primes folder, there's going to be this libabi3 so file. This is basically that Rust code taken and published as a binary containing the fast Rust code at the machine code level. All right? So maturin, during the build process, ultimately all it does for you, it generates that libabi.so for you, and that so has the right format that the Python importer can actually discover it and pull it in. And now you see why it was important for us when we specified the configuration to specify where we want to put it, and we say primes_.lib. It's because it generated it under that location. Okay? So, what does PyO3 offer to you? Well, it does some of basically handles the Rust panic. As you said beforehand, in Rust, there is no such thing as exception. So if the code fails for whatever reason that you've written, it's going to raise the panic. Rust or the PyO3 will then translate that into a base exception in your Python interpreter. You could catch it, but you should not. Because again, the Rust interpreter doesn't do anything after it comes to find panic. So you're going to get into weird cases if you do that. Another thing it's going to do is going to manage the memory for you. It's going to manage the reference count between the two boundaries. And more importantly, going to do the argument parsing for you. If you pass a Python integer as an argument to a method, it's going to translate it into Rust. And similarly, the return value is going to be translated automatically for you into Python types. So you don't have to worry about how that part happens that much. And finally, actually calls the Rust user code whenever you invoke it. Okay? So, with all this information, I hope all of you are ready to run and write some Rust code. But first, let me tell you some complications that you're going to run into. The first thing is that you have to think about types. In Python, it's great. There's one integer, handles any size of number. Rust is not like that. In Rust, you have to say it. So how big can this number be? You see, Python's one integer can be translated to basically those, well, I don't even know, 12 integer types. So you'll have to think about which one you want to pick. Another thing, there is an overhead to cross between the languages. While this is small, so you shouldn't really write very simple code to call into the Rust, because then the overhead will be more than the gain. Also, you're going to get the biggest bang of buck for CPU-bound operations. If you're calling out to a web server, don't try to do it in Rust, because you're not going to get much benefit. Similar for system I/O operations. And you're also going to run occasionally into systems where you're going to find some Rust library that's not supported on various operating systems. Remember, Rust compiles down to binary machine code. That means that if you get the latest, I don't know, latest ARM64 Raspberry CPU, it might not work on that because it has platform limitations. Yes, I heard all of you speaking. So what about Cython? Why I don't use Cython? And as you can see from here, this was the Rust code. This is going to be the Cython code. It's a bit more Pythonic, a bit ugly, but still works. Well, the answer is there's no reason why you shouldn't use Cython. As you can see here, Cython and Rust are basically the same performance gain at the end of the day, more or less. So if you want to write Cython, good luck. More power to you. But you can also do it in Rust now if you want, okay? So obviously, if you write Cython, you're not going to be able to use all the rich Rust ecosystem functionality, but maybe you don't want to deal with that. And Cython tends to be a bit more friendly when it comes to supporting weird, archaic platforms. All right. So now let me tell you about, let me use the next minute to vent my frustrations with Rust. All right. So one of the things that you will have to deal with it as any new Rust learner is to fight the borrow checker. This is basically, you want to make the compiler happy. In Python, you can write whatever you want. It will run, maybe throw an exception, but it will run. In Rust, if you write some code and the compiler is not happy, it will not even start. So you might spend an hour just trying to run it and then see that it doesn't work. All right? Another thing, the debugger is not as powerful as in Python. It's great in Python. You can put a breakpoint anywhere. You can put like complex expression. You can call two methods, add it together, all that kind of stuff. Forget it in Rust. In Rust, basically, you can call inspect a variable or something, or maybe call a method if you're lucky, depending on the stars. But that's about it. That means that most people, Rust developers I talk with, they will tell them, like, so what do you do to debug your code when it doesn't work? Because I don't know. I'm not that good to write perfect code. I have to debug occasionally. They say, well, I just use println. To which my answer is, great, but to use println, I need to recompile the application. It takes time. I need to restart the application, feed it to the right information to it, not to even debug the application, or maybe I spend an hour where in Python in 10 minutes I might have finished. So, but yeah, there's some trade-off here. The compiler can be slow. This kind of like ties into the debuggability of it. Especially Rust, everything is compiled from source. This is a plus if you hate packaging, because you don't have to publish binary packages. But then it means that anyone who wants to use your library will spend the first half an hour compiling all the dependencies whenever they start a new project. And occasionally, you're going to have this issue when some dependency of yours fails to build on a random downstream dependency. There's nothing more disappointing when you write your code, works great on macOS, then you publish it to the CI, and you see that Windows doesn't support it, one of the dependencies. And I'm like, OK, I guess I have to throw out that library, find another one that works. All right. Long story short, when you're going to start doing Rust, expect the bumpy learning curve. What this means, you're going to feel just as many times happy as many times you're going to be disappointed and sad. That's fine. The good thing is if you keep at it and persist at it, after a few days, weeks, months, you're going to reach nirvana up there in the top left corner. But it's not going to be a smooth ride or a straight ride. All right? Here you can see some reference pages. When it comes to IDEs, I find that Rust Rover works the best, offers the most IDE-like functionality. VS Code also works, but it's a bit less powerful. But I think Rust Rover, especially at more advanced functionality, requires a license. So caveat there. Thank you.